Hello everyone, I am Amareshwar from BS Physics IIT Roorkee. In this video, I'll be presenting my CWS project for the course Fundamentals of AI. The name of my project is Pneumonia Detection and Classification. Pneumonia is a respiratory disease that causes inflammation in the lungs. It can be due to infections by bacteria, viruses, or fungi. Although chest X-rays are widely used for diagnosis, manual interpretation is often slow and is dependent on expert radiologists, which can be challenging in some situations. The solution is deep learning models like CNNs have proven to be a valuable tool for assisting radiologists for pneumonia detection. The objective of this project is to construct a CNN model which can accurately predict whether the given chest X-ray is either normal, bacterial, or viral pneumonia. It also aims to assist radiologists in detection of pneumonia from X-rays more accurately and more quickly. The first step in the project is data collection. I have used a Kaggle pneumonia dataset for my project. So the dataset contains three folders, one for each class. Each class contains more than 3000 images, and you can see that the dataset is balanced. On opening the folder, we can see various images related to the class, but each class is not divided into training, testing, and validation dataset. So first, we import the dataset using the Kaggle API. Then, we split the data into training, testing, and validation. We use Shuttle for copying images, OS and random module for splitting the images and storing them in new directory. So we create new folder for training, validation and testing for each class. Each class For each class 70% is given for training, 15% for validation and 15% of the images for testing. In the next step, we apply image preprocessing to all the images. Each image is resized to 224 cross 224 size. Then we apply random horizontal flip for data augmentation. And then each image is converted to a tensor and the pixel values are normalized. Then I used datasets and data loader for efficiently loading and managing the data. The data is fed training into the neural network in batches of 32 images. The next step is training the CNN. Before the training, let us see the CNN architecture. The CNN performs two main tasks. The first is feature extraction by a group of convolution layers and then classification by the fully connected layer. The CNN also has many components. The first is kernel. A kernel is nothing but a filter which extracts the features from the image. The process is called convolution. In the convolution, we multiply the value of the kernel with the corresponding value of the image patch and then add all the values to get the convolution. The result is also called feature map. The feature map is then passed through the ReLU activation function. The use of ReLU is it allows the convolution layer to extract complex features from the data by introducing non-linearity between convolution layers. Next is stride. Stride tells us about the amount by which kernel moves after a convolution operation. If the kernel moves by 1 pixel, then stride is 1. The kernel may move horizontally or vertically along the image. If the kernel moves by 2 units, then stride is 2. Next is padding. Padding allows us to extract low-level features. This is done by retaining the original size of the image. For this, we add an extra layer of pixels to the image and then convolve with the filter. The next operation is pooling. Pooling allows to retain the features of an image while also reducing the size of an image. Max pooling is used to retain the dominant features of an image. It is a simple operation which when performed like the green region represents the max pooling on the green region of the image. When max pooling is performed on this region, it takes the maximum value. Here it is 12. So it takes 12. For the purple region, the maximum value is 7. So we get 7 and so on. The average pooling, as the name suggests, takes the average. For the green region, it takes the average of these four numbers and we get 9. The same goes for the other layers, other colors. Next is flattening. As the image is stored as a multi-dimensional tensor, the flattening operation converts the multi-dimensional tensor into one dimension. The flattened layer is fed as input to the fully connected layer. The fully connected layer looks similar to the ANN. In the beginning, the weights and bias of fully connected layer are randomly initialized. When the input flows from input layer to output layer, it is called forward propagation. The output is a label. The predicted label is compared to the actual label of the image. The loss is calculated with the help of loss function, and then gradients are calculated in the opposite direction, which is called backward propagation. In the backward propagation, the gradients calculated determine how much each weight or bias contribute to the loss. With the help of optimizer, we update the weights. At the end of the CNN, we use a sigmoid function, which converts raw outputs to probability. The sigmoid function gives the probability of an image belonging to a particular class. So this is the CNN model which I have built. It consists of three convolution layers and a fully connected layer. We don't need to add a softmax function at the end of the CNN because the categorical cross entropy loss which we define already has an inbuilt softmax function. After building the CNN, we initiate an instance of CNN and then we define the number of epochs and the learning rate. And after that, we also define the loss function and optimizer which is to be used in the model training. Here I have defined accuracy which will also be used in the training. For visualization purpose, I have defined these lists to keep track of the training process. The model is trained on the training data and validated on testing data for each epoch. The model with best validation accuracy is stored in this part. As you can see, for each epoch, the loss has significantly decreased and the training and validation accuracy have increased. The model with the best validation accuracy is 96.24%. So plotting the training validation accuracies and we get this curve. So we can clearly see when the accuracy increases, the validation accuracy also increased. So there are no signs of overfitting, or we can clearly identify overfitting when the training accuracy increases, the validation accuracy decreases. They both diverge. So for evaluation purpose, I have imported confusion matrix and accuracy score from scikit-learn library. And this code helps us to evaluate the model. The model is evaluated on unseen data, which is the test data. So I have loaded a new instance of the CNN model, and I have loaded the best parameters to that model. The evaluation gives 96.18% accuracy, which is which shows that the model generalizes well on the unseen data. And also from the confusion matrix, we can see that the true positivity rate for a particular class, which means that the true label of the class and the predicted label is very much higher than the values in the other cells. I have also built a predictive system which will help to classify whether an uploaded X-ray is viral pneumonia, bacterial pneumonia, or normal. So I have downloaded an image from Google, which is a normal chest X-ray. So the model also predicted normal. Here, the confidence is nothing but the output of the softmax function. So, yeah, thank you for watching.